It was March 1995. The setting was the University of Southern California during an annual physics conference called Strings 95. The field of string theory was in a weird place. For about a decade since the first superstring revolution of 1984, physicists had been working with 5 different competing versions of the theory. There was type I, type IIA, type IB, and 2 flavors of heterotic string theory. They all described a universe with 10 dimensions where fundamental particles were tiny vibrating strings, but they were all mathematically distinct. You had to pick one, and nobody knew which one was right. It felt like a messy, incomplete picture. Then Edward Witten of the Institute for Advanced Study took the stage. He wasn't even scheduled to give a major talk, but what he presented was a bombshell. He proposed that these 5 different theories were not competitors at all. They were just 5 different perspectives on a single deeper theory that lived in 11 dimensions. Or he didn't have a full name for it, so he called it M theory. The M was a bit of a joke, standing for mystery or magic or mother of all theories. He showed how, through mathematical relationships called dualities, if you tweaked the parameters of one theory, it would transform into another. It was like realizing that 5 different descriptions of an elephant, one of the trunk, one of the leg, one of the tail, were all describing the same animal. The biggest new idea was that M theory didn't just contain strings, it also contained higher dimensional objects he called membranes, or brains for short. Our entire 4-dimensional universe, he suggested, could be one of these brains floating in a larger 11-dimensional space. This lecture kicked off the second superstring revolution. It took the fragmented world of string theory and united it under a single, strange, and much larger framework. The idea that our reality is just a slice of a higher dimensional reality wasn't just sci-fi anymore. It was now at the heart of the leading candidate for a theory of everything. Number 23, the core idea is just tiny vibrating strings. A single string is thought to be around 10 to the power of 35 meters long. This is the Planck length, the smallest possible distance in physics. If you blew up an atom to be the size of our entire solar system, a string would be about the size of a tree. The different vibrations of these strings are what we see as different particles. At the very bottom of everything, there are no particles, no little billiard balls like electrons or photons. They're just strings. This is the fundamental claim of string theory. It replaces the 0-dimensional point particle of standard physics with a 1-dimensional vibrating line of energy. It's a simple change, but it fixes a lot of problems. Point particles cause mathematical headaches. Because they have no size, calculations involving them, especially in gravity, often result in infinite values, which is physics speak for, we broke the math. A string, by having a tiny but non-zero length, smooths out these interactions. The math suddenly starts working. Think of a guitar string. It can vibrate at different frequencies. Each frequency produces a different musical note. A string in string theory works the same way. One vibrational pattern, one note, might appear to us as an electron. A different vibration might look like a photon. A third might be a quark. All the different particles we see in the universe, the entire zoo of matter and forces, are just different tunes being played on these fundamental strings. The mass of a particle is just the energy of the vibration. The charge of a particle is also determined by how the string vibrates. It's a beautifully simple concept. Instead of dozens of fundamental particles, you have just one thing, the string. There are 2 basic types of strings. Open strings have 2 distinct endpoints. Closed strings form a continuous loop. This distinction is crucial. The particles that make up matter, like electrons and quarks, are thought to be open strings. The particles that carry forces are also mostly open strings, but there's one big exception. One specific vibrational mode of a closed string has a unique set of properties. It has zero mass and a specific amount of spin. These are the exact properties of the graviton, the hypothetical particle that carries the force of gravity. This was a huge moment for physicists. In other theories, gravity is the odd one out. It's incredibly hard to unify with the other forces, but in string theory, gravity isn't an afterthought. The existence of the graviton is a direct, unavoidable prediction of the theory. You can't have a theory of strings without also having a theory of gravity. It just falls out of the math naturally. Number 22. Our universe might have 10 or 11 dimensions. The first viable string theory, called bosonic string theory, required a universe with 26 dimensions to be mathematically consistent. Later versions incorporating a concept called supersymmetry reduced this number to 10. The unified M-theory, which came later, operates in 11 dimensions. We only experience 4 dimensions, 3 of space length, width, height, and 1 of time. So where are the others? This is one of the wildest and most famous parts of string theory. The theory doesn't work in our familiar 4 dimensions. The equations simply fall apart. They need more room to maneuver for the math to be consistent and to avoid bizarre predictions like faster than light particles or probabilities that are negative. The universe must have extra spatial dimensions. In the most popular versions of the theory, that means 6 extra dimensions of space we can't see. The standard explanation for why we don't see them is called compactification. The idea is that the extra dimensions are curled up or compactified into an incredibly tiny space. They are so small that we can't detect them with our current technology or even perceive them at all. The classic analogy is a garden hose or a tightrope. From far away, it looks like a one-dimensional line. You can only move forward or backward along its length. But if you get very close, you see it has a second dimension, the circular part you can move around. An ant walking on the tightrope could move forward, backward, or loop around its circumference. For the ant, it's a 2-dimensional world. For us, from a distance, it's just 1. String theory proposes that the extra 6 dimensions are like the tiny circular part of the tightrope. They exist at every point in our familiar space, but they are curled up on a scale smaller than an atom. And M-theory bumped this up to 7 extra spatial dimensions for a total of 11 space-time dimensions. This 11th dimension was a crucial breakthrough. It was the key that allowed Edward Witten to show that the 5 competing 10-dimensional string theories were all connected. He demonstrated that the 11th dimension's size was related to the strength of the interactions in the 10-dimensional theories. When this dimension is small, you get one version of string theory. When it's large, you get another. This extra layer of reality provided the unifying perspective that the field desperately needed in the mid-1990s. The idea is profound. The laws of physics as we see them might depend on the geometry of dimensions we can't see. Number 21. The extra dimensions are curled up incredibly small. The specific shapes in which the extra dimensions can be curled up are known as Calabi-Yau manifolds. There are a staggering number of possible Calabi-Yau shapes, with estimates ranging from 10 to the power of 500 to even higher. Each one of these shapes would result in a universe with its own unique set of physical laws and fundamental constants. It's not enough to just say the extra dimensions are curled up. The shape of that curling matters a lot. It turns out the geometry of these hidden dimensions dictates the physics we see in our large extended dimensions. You know, the way the dimensions are twisted and folded determines things like the masses of electrons and neutrinos, the strength of the electromagnetic force, and how many generations of fundamental particles exist. All the numbers in the standard model of particle physics, which we have to measure and plug into our equations by hand, would, in principle, be determined by the precise shape of these compactified dimensions. This is where Calabi-Yau manifolds come in. These are complex, six-dimensional geometric shapes that have the right mathematical properties to serve as the home for the hidden dimensions. They are named after mathematicians Eugenio Calabi and Xing-Tung Yao, who studied them long before they were applied to string theory. The properties of these shapes are incredibly intricate. They have holes, twists, and cycles. The number of holes, for example, is related to the number of families of particles we see. Our universe has three families of matter particles. The first includes the up quark, down quark, and electron. The other two are heavier copies. This suggests that the Calabi-Yau manifold corresponding to our universe should have three holes. This leads to both a great hope and a great frustration for string theory. The hope is that if we could find the one correct Calabi-Yau shape for our universe, we could calculate all the fundamental constants from first principles. We could finally explain why, for instance, an electron has the mass it does. It would be the ultimate triumph of physics. The frustration is the sheer number of possibilities, with 10 to the 500 or more potential shapes. Finding the right one is like searching for a single specific grain of sand on all the beaches of the world. This is the origin of the string theory landscape. It suggests that our universe, with its specific laws, might just be one of a vast number of possible universes, each with a different Calabi-Yau geometry and thus different physics. We just happen to live in the one with the right properties for life to exist. In number 20, every particle has an unseen superpartner. Supersymmetry, a key ingredient in most string theories, predicts that for every known particle there exists a corresponding superpartner. For every fermion a matter particle, like an electron or quark, there is a corresponding boson of force-carrying particle. For every boson, like a photon, there is a corresponding fermion. The superpartner of an electron is called a selectron. The partner of a photon is a photino. This idea, known as supersymmetry or SUSY, wasn't originally part of string theory. It was developed in the 1970s as a standalone concept, but it turned out to be exactly what string theory needed. The original version of string theory, bosonic string theory, had a major flaw. It predicted the existence of tachyons, particles that travel faster than light and have imaginary mass, which would destabilize the universe. Incorporating supersymmetry into the theory fixed this problem. It elegantly canceled out the mathematical terms that led to tachyons. This new, improved version was called superstring theory. Supersymmetry creates a deep and elegant link between the two fundamental classes of particles, fermions, and bosons. Fermions are the building blocks of matter. They obey the Pauli exclusion principle, which means no two of them can occupy the same quantum state. This is why matter is solid and takes up space. Bosons carry forces. They have no problem piling on top of each other in the same state, which is how you can get a powerful laser beam made of countless photons. Supersymmetry says these two groups are two sides of the same coin. Every fermion has a boson superpartner and vice versa. The names are a bit clunky. The partners of quarks are squarks, the partner of the Higgs boson is the Higgsino, and partners of force carriers like the W and Z bosons are YNOs and XENOs. If supersymmetry is real, where are all these superpartners? We've never detected a single one. The theory explains this by suggesting that superpartners are much heavier than their standard counterparts. The symmetry is broken. At the high energies of the very early universe, the symmetry was perfect, and particles and their superpartners had the same mass. As the universe cooled, this symmetry broke, and the superpartners became very massive and unstable. This is why we need powerful particle accelerators like the Large Hadron Collider LHC to find them. The LHC was built in part with the hope of discovering supersymmetric particles. So far it has found none, which has been a major blow to the theory and has forced physicists to reconsider some of their assumptions. The search continues, but the window for finding simple versions of supersymmetry is closing. Number 19, our universe is a hologram. The holographic principle, first proposed by Gerard and Hooft in 1993, and later developed by Leonard Susskind, suggests that the information contained in a volume of space can be completely described by a theory that lives on the boundary of that region. This is like a 3D hologram being encoded on a 2D surface. In 1997, physicist Juan Maldacena discovered a concrete mathematical example of this principle within string theory, linking a theory of gravity in a 3D volume to a quantum field theory on its 2D boundary. This is one of the most mind-bending ideas to come out of string theory research. It suggests that the three-dimensional reality we experience might be an illusion, a projection of information stored on a distant, two-dimensional surface. The world you see around you, with its depth and texture, could be encoded on a cosmic screen at the edge of the universe. The idea grew out of the study of black holes. Jacob Bekenstein and Stephen Hawking discovered that the entropy of a black hole, a measure of its information content, is not proportional to its volume, as you might expect. Instead, it's proportional to the surface area of its event horizon. This was a strange result. It's as if all the information about everything that ever fell into the black hole is stored on its 2D surface, not within its 3D bulk. This led to the holographic principle, the idea that this might be a general property of the universe, not just of black holes. The maximum amount of information you can cram into any region of space is determined by the area of its boundary, not its volume. If you try to pack in more information, it will collapse into a black hole whose surface area is exactly big enough to hold that information. Juan Maldacena's 1997 discovery, called the ADES-CFT correspondence, gave this idea a solid mathematical footing. He found a precise duality, a mathematical equivalence, between two very different-looking theories. One was a string theory describing gravity in a five-dimensional, saddle-shaped spacetime called anti-de Sitter space ADS. The other was a four-dimensional quantum field theory similar to the one describing the strong nuclear force that lived on the boundary of that spacetime. Everything that happens in the 5D world with gravity can be perfectly described by the 4D world without gravity, and vice versa. They are two different languages describing the same reality. This has become one of the most powerful tools in theoretical physics. It allows physicists to tackle incredibly difficult problems in gravity by translating them into simpler problems in quantum field theory, and it suggests that space-time and gravity themselves might not be fundamental, but rather an emergent holographic phenomenon. Number 18, the universe exists on a giant membrane. In M-theory, the version of string theory that operates in 11 dimensions, our entire four-dimensional universe, 3 space, 1 time could be a brane. A brane is a physical object that can have any number of dimensions. A 0 brane is a point. A 1 brane is a string, and a 2 brane is a membrane. Our universe could be a 3 brane. This brane is floating in a higher dimensional space called the bulk. This brane world scenario completely changes our picture of the cosmos. It suggests that our universe is not all there is. There could be other branes, other universes floating parallel to our own in the higher dimensional bulk. These branes could be just millimeters away from us in the extra dimensions, but we would be completely unaware of them. Why? Because most particles and forces are stuck to our brane. The idea is that the open strings that make up matter and the forces of the standard model electromagnetism, the weak and strong nuclear forces, have their endpoints attached to our 3 brane. They can slide around on the brane, but they can't leave it. They are trapped in our 4-dimensional slice of reality. This offers a novel explanation for a long-standing puzzle why gravity is so much weaker than the other fundamental forces. The force of gravity is about a trillion times weaker than the electromagnetic force. A simple fridge magnet can defeat the gravitational pull of the entire Earth. In the brane world picture, this is explained by the fact that gravity is not stuck to our brane. Gravity is mediated by the graviton, which corresponds to a closed loop of string. Since it has no endpoints to anchor it, the graviton is free to travel not just along our brane, but also off it. into the bulk. Gravity leaks into the extra dimensions. The gravitational force we feel in our universe is just a small fraction of its true strength because most of it has dissipated into the vastness of the higher dimensional space. This idea, developed in models like the Randall-Sundrum model in 1999, is potentially testable. If extra dimensions are large enough, high-energy particle collisions at the LHC could create gravitons that fly off into the bulk, carrying energy with them. We would detect this as missing energy in the experiment, a possible signature of these hidden dimensions. Number 17, the Big Bang, was two universes colliding. A popular brane-world model called the ekpyrotic universe, proposed in 2001 by Paul Steinhardt, Justin Khoury, Bert Overoot, and Neil Turok, suggests that the Big Bang was not the beginning of time. Instead, it was the result of a collision between our brane universe and another parallel brane universe moving through the bulk. This collision released a tremendous amount of energy, heating our universe and creating the matter and radiation we see today, setting the stage for cosmic expansion. This is a radical alternative to the standard Big Bang theory. The standard theory has a singularity problem, a point at the very beginning where density and temperature are infinite and the laws of physics break down. The ekpyrotic model, the name comes from a Greek word for a cosmic fire, avoids this singularity. It proposes a cyclical universe. The two branes collide, creating a bang. They then move apart and our universe expands and cools. Over trillions of years, the universe empties out and becomes cold and dark. But the branes, pulled by a force connected to dark energy, eventually start moving toward each other again. They collide once more and the cycle begins anew. In this picture, the universe has a history that stretches back long before our Big Bang. Time is infinite. The hot, dense state we call the Big Bang is just a recurring event in an endless cycle of cosmic rebirth. This model also offers a different explanation for some key features of our universe. For example, the universe is incredibly uniform on large scales, a feature usually explained by a period of rapid inflation just after the Big Bang. In the ekpyrotic model, this uniformity is explained by the branes being very smooth and parallel before they collided. The slight ripples and variations in their surfaces before the collision would be imprinted on our universe as the seeds for galaxy formation. The idea is still speculative, but it shows how the concept of branes can provide completely new ways of thinking about our cosmic origins, replacing the mysterious singularity with a more physical, albeit equally spectacular event. Number 16, the multiverse is real and has 10 raised to the power of 500 universes. The string theory landscape is the idea that there isn't just one single vacuum state or set of physical laws predicted by string theory. Instead, because there are so many ways to compactify the extra dimensions, at least 10 to the power of 500 different Calabi-Yau shapes, there is a vast landscape of possible universes. Each point in this landscape corresponds to a different vacuum, with its own distinct set of physical laws, constants, and particles. Our universe is just one of these possibilities. This is perhaps the most controversial outcome of string theory. The original hope was that the theory would uniquely predict the laws of our universe. Physicists hoped that the mathematics would be so constrained that there would be only one possible way for a consistent universe to exist, and its properties would match what we observe. The landscape picture shatters that hope. It suggests that almost any kind of universe is possible. Some might have a much stronger force of gravity, some might have no electrons, most would be utterly inhospitable to life. This has led to the adoption of the anthropic principle by some physicists. The reasoning goes like this. We find ourselves in a universe with a very specific, fine-tuned set of properties that allow for stars, planets, and life to exist. The cosmological constant, for example, is incredibly small, far smaller than theory predicts. If it were much larger, the universe would have flown apart before galaxies could form. The anthropic explanation for this is that we could only exist in a universe that has these life-friendly properties. Out of the 10 raised to the power of 500 possible universes in the landscape, only a tiny fraction are habitable. It's no surprise that we find ourselves in one of them, just as it's no surprise that we find ourselves on a planet with liquid water. We couldn't be anywhere else. Many physicists are deeply uncomfortable with this line of reasoning. They feel it's a cop-out, a retreat from the goal of making unique, testable predictions. It makes string theory seem less like a predictive science and more like a framework that can explain anything after the fact. The debate over the landscape and the anthropic principle is one of the biggest philosophical divides in modern physics. Does string theory predict a multiverse of possibilities, or is the landscape a sign that we are missing a crucial piece of the puzzle, a principle that will one day allow us to select the one true vacuum that describes our world? Number 15, black holes are just really messy fuzzballs of string. According to the fuzzball proposal, developed by Samir Mathur and his colleagues around 2002, a black hole is not a singularity surrounded by an empty event horizon, as described by general relativity. Instead, a black hole is a tangled, messy ball of strings, brains, and other quantum stuff. The entire volume of what we think of as a black hole is filled with this fuzz. There is no singularity at the center and no sharp event horizon. The surface of the fuzzball is the effective event horizon. This idea directly addresses one of the most profound paradoxes in physics, the black hole information paradox. Stephen Hawking showed in the 1970s that black holes are not truly black. They slowly radiate energy, now called Hawking radiation. This radiation is predicted to be perfectly thermal, meaning it contains no information about what fell into the black hole. This violates a fundamental principle of quantum mechanics, which states that information can never be destroyed. If a book falls into a black hole, the information contained in its pages should, in principle, be recoverable. But if the black hole evaporates into purely random thermal radiation, that information is lost forever. The fuzzball proposal solves this by getting rid of the feature that causes the problem, the singularity and the perfectly empty event horizon. In the fuzzball picture, when matter falls onto a fuzzball, it gets incorporated into the complex tangle of strings. Its information is not lost. It becomes part of the fuzzball's structure. The Hawking radiation that comes off is not perfectly thermal. It contains subtle correlations that hold the information about what fell in. It's like burning a book. In practice, it's impossible to reconstruct the book from the smoke and ash, but in principle, all the information is still there, just scrambled. The fuzzball idea also connects to the counting of black hole microstates. In 1996, Andrew Strominger and Kumrun Vafa used string theory to calculate the entropy of a certain type of black hole. They modeled the black hole as a collection of strings and brains and counted the number of ways these components could be arranged to produce the same overall mass and charge. The number they calculated perfectly matched the Bekenstein-Hawking formula for the black hole's entropy. This was a landmark success for string theory, suggesting it had the right tools to describe the quantum nature of black holes. The fuzzball proposal is a physical interpretation of what these microstates are. They are all the different possible configurations of the tangled ball of string. Number 14, dark matter could be a particle from another dimension. A significant portion of the universe, about 27%, is made of dark matter. We can't see it, but we know it's there because of its gravitational effects on galaxies and galaxy clusters. String theory offers several candidates for what this mysterious substance could be. One of the most popular is the lightest supersymmetric particle, LSP. In many versions of supersymmetry, the LSP is stable, electrically neutral, and interacts very weakly with normal matter. These are the exact properties required for a dark matter particle. In most supersymmetric theories, there's a rule called R-parity conservation. This rule essentially states that superpartners must be created or destroyed in pairs. A consequence of this is that the lightest superpartner cannot decay into normal particles because there's nothing lighter for it to decay into. It is therefore stable. If these LSPs were produced in large numbers in the early universe, they would still be around today, forming a vast invisible halo around galaxies. The most common candidate for the LSP is the neutralino, a quantum mixture of the superpartners of the photon, the Z boson, and the Higgs boson. For years, experiments have been trying to detect neutralinos, either by spotting them directly as they bump into atomic nuclei in underground detectors, or by creating them in particle colliders. So far, they have found nothing. But string theory offers other, more exotic possibilities. One idea comes from the brane world scenario. It's possible that dark matter is made of particles that live on a parallel brane, separate from our own. We can't see these particles because they don't interact with light, which is stuck on our brane. But since gravity can travel between branes, we would feel the gravitational pull of the matter on that other brane. And dark matter could literally be matter in a shadow universe gravitationally linked to our own. Another possibility involves stringy relics from the early universe. Perhaps dark matter is composed of particles associated with the vibrations or geometry of the curled-up extra dimensions, sometimes called Kaluza-Klein particles. These would be heavier versions of normal particles that get their extra mass from momentum in the extra dimensions. Like the LSP, these particles could be stable and interact weakly, making them viable dark matter candidates. Number 13, dark energy, is a consequence of the string landscape. Dark energy is even more mysterious than dark matter. It makes up about 68% of the universe and is causing the expansion of the universe to accelerate. The simplest explanation is the cosmological constant energy density of empty space itself. The problem is that our best theories of quantum mechanics predict a value for this energy density that is about 10 to the power of 120 times larger than what we observe. This is the worst prediction in the history of physics. String theory doesn't solve this problem directly, but it offers a potential framework for understanding it through the landscape. The vacuum energy, or cosmological constant, is another property that is determined by the shape and structure of the compactified extra dimensions. Each of the 10 raised to the power of 500 possible Calabi-Yau geometries in the landscape would have its own value for the cosmological constant. The vast majority of these would have a huge value, either positive or negative. A large positive value would cause the universe to rip itself apart instantly. A large negative value would cause it to collapse in a fraction of a second. The string landscape, therefore, contains a huge number of possible universes, almost all of which are duds. However, with so many possibilities to choose from, it's statistically possible that a few of them would, just by chance, have a value for the cosmological constant that is incredibly close to zero. The anthropic argument then comes back into play. We must be living in one of these rare, fine-tuned universes because they are the only ones that last long enough for galaxies, stars, and observers to form. While many physicists dislike this explanation, it's one of the few ideas that can grapple with the absurdly small value we observe. It turns a problem of calculation into a problem of statistics. We don't need to explain why the value is so small in our universe. We just need to accept that our universe is one of the rare ones in the multiverse where it happens to be small. This is a profound shift in thinking. It suggests that the value of the cosmological constant may not be a fundamental number we can derive from first principles. Instead, it might be an environmental variable, like the temperature of a planet. Different universes have different values, and we just happen to live in a comfortable one. Number 12, space-time itself is not fundamental. One of the deepest insights from string theory, particularly from the holographic principle and the ADS-CFT correspondence, is that space-time, as we know it, might be an emergent phenomenon. It's not a fundamental part of reality's bedrock. Instead, it's a collective effect that arises from more fundamental underlying quantum information. This is similar to how the properties of a fluid like temperature and pressure are not fundamental properties of individual water molecules. They are emergent properties that only make sense when you have a huge collection of molecules acting together. The ADS-CFT correspondence provides a concrete example of this. It shows a perfect equivalence between a theory with gravity and a dynamic spacetime, the bulk theory, and a quantum theory without gravity, and with a fixed static spacetime, the boundary theory. This suggests that the extra dimension of space and the entire fabric of gravity in the bulk theory can be built from the quantum interactions of the particles on the boundary. Spacetime and gravity emerge from the entanglement of quantum bits of information. A more recent idea connecting quantum information and spacetime is the ER=Sepper conjecture proposed by Leonard Susskind and Juan Maldacena in 2013. EPR stands for an Einstein-Podolsky-Rosen pair, a pair of entangled quantum particles. ER stands for an Einstein-Rosen bridge, which is a wormhole. The conjecture proposes that these two seemingly unrelated concepts are actually the same thing. When two particles are quantumly entangled, they are connected by a microscopic wormhole. This is a shocking idea. It connects the strange, spooky action at a distance of quantum mechanics directly to the geometry of spacetime. It suggests that the very structure of space is woven from the threads of quantum entanglement. If you have a complex network of entangled particles, you get a complex curved spacetime. In this view, spacetime is the geometric manifestation of the quantum information connecting its constituent parts. The universe isn't a stage on which quantum mechanics happens. The universe is built out of quantum mechanics. Number 11, wormholes connect entangled particles. The ER=CPR conjecture, proposed in 2013, posits that any pair of quantumly entangled particles is connected by a microscopic wormhole or an Einstein-Rosen bridge. This suggests a deep and previously unsuspected connection between the geometry of spacetime wormholes and the fundamental properties of quantum mechanics entanglement. While these wormholes are not traversable, meaning you can't send signals through them faster than light, their existence would fundamentally change our understanding of what spacetime is made of. Or quantum entanglement is a phenomenon where two or more particles become linked in such a way that their fates are intertwined, no matter how far apart they are. If you measure a property of one particle, you instantly know the corresponding property of the other. Einstein famously called this spooky action at a distance. The ER=CPR idea provides a potential geometric explanation for this spookiness. The two particles aren't communicating faster than light. They are connected through a shortcut in the fabric of spacetime itself. The wormhole is the physical link that constitutes their entanglement. This idea has profound implications for black holes and the information paradox. Consider the Hawking radiation emitted by a black hole. An emitted particle is entangled with its partner particle that fell into the black hole. As the black hole evaporates, it emits more and more particles, each entangled with a partner inside. This creates a complex web of entanglement between the radiation outside and the black hole's interior. The ER=CPR conjecture suggests that this web of entanglement corresponds to a complex network of wormholes connecting the inside of the black hole to the radiation far away. This could be the key to how information gets out of a black hole. The information isn't lost inside a singularity. It's encoded in the entanglement between the interior and the exterior, and this entanglement has a geometric reality as a network of wormholes. The black hole interior is, in a very real sense, being reconstructed outside of itself through these connections. It's a radical proposal that weaves together general relativity, quantum mechanics, and information theory in a way that only seems possible within a framework like string theory, where spacetime is flexible and emergent. It means that the connectivity of space is not fixed, but is determined by the quantum relationships between the things within it. Number 10. Some versions of string theory are secretly the same. One of the most powerful concepts in modern string theory is duality. A duality is a situation where two different looking physical theories turn out to be mathematically equivalent. They are just two different descriptions of the same underlying reality. The discovery of these dualities in the 1990s is what led to the second superstring revolution and the proposal of M-theory. There are two main types of duality, T-duality and S-duality. T-duality relates string theories in which the extra dimensions are curled up into circles of different sizes. It makes the bizarre prediction that a universe with a very small, curled-up dimension of radius r is physically indistinguishable from a universe with a very large, curled-up dimension of radius 1r in appropriate units. This is completely counterintuitive from the perspective of point particles. For a particle, a small box and a big box are obviously different. But for a string, things are different. A string can not only move around the curled up dimension, but it can also wrap around it. In a small dimension, the energy required to move is high quantum mechanics says momentum comes in discrete packets, and small spaces mean big momentum packets, but the energy required to wrap the string around the dimension is low. In a large dimension, the opposite is true. Moving is low energy, but wrapping is high energy. T-duality shows that if you swap the moving energy modes with the apping energy modes, the physics of a small radius universe becomes identical to the physics of a large radius universe. This implies there is a minimum possible length in the universe, the Planck length. If you try to probe a distance smaller than that, the physics just looks like you're probing a larger distance. S-duality is even more profound. It relates a theory with a strong interaction strength, a large coupling constant, to a different theory with a weak interaction strength, a small coupling constant. This is an incredibly useful tool. Calculations that are impossibly difficult to do in a strongly coupled theory can be translated into easy calculations in a weakly coupled one. Before M-theory, there were 5 main string theories. S-duality showed, for example, that the type I string theory at strong coupling is equivalent to one of the heterotic string theories at weak coupling. This was a crucial clue that these supposedly different theories were connected. Edward Witten used these dualities to argue they were all just different corners of the parameter space of a single 11-dimensional M-theory. Number 9, giant cosmic strings, could be stretching across the universe. While the fundamental strings of string theory are subatomically small, some models predict the existence of macroscopic cosmic strings. These would be incredibly thin, but astronomically long filaments of energy, leftovers from the phase transitions in the very early universe. They are essentially defects in the fabric of space-time, similar to the cracks that form when water freezes into ice. These strings could stretch across vast distances, potentially even across the entire observable universe. These cosmic strings would be unimaginably dense. A string just 1.6 kilometers long would have a mass equivalent to the Earth. Because of their immense mass and tension, they would have dramatic gravitational effects. If a cosmic string were to pass through a galaxy, it could disrupt star orbits. More significantly, they would warp the space-time around them. The light passing on either side of a cosmic string would be bent, leading to a specific gravitational lensing effect. Instead of creating multiple distorted images of a distant object like a galaxy cluster does, a cosmic string would create 2 identical undistorted images of the object. Searching for these double images of distant quasars is one of the main ways astronomers are hunting for cosmic strings. Cosmic strings would also be powerful sources of gravitational waves. As these long strings wiggle and kink, and as loops of string break off and oscillate, they would radiate energy in the form of ripples in spacetime. This would create a stochastic background of gravitational waves across the universe. Gravitational wave detectors like LIGO and future experiments like LISA could potentially detect this background hum, which would be a smoking gun signature of string theory physics operating on a cosmic scale. So far, no definitive evidence for cosmic strings has been found, either from lensing or gravitational waves, which has placed tight constraints on the models that predict them. But the search continues for these exotic relics of the earliest moments of creation. Number 8. The arrow of time might be explained by brains. Why does time only move forward? This is one of the deepest questions in physics. The fundamental laws of physics, for the most part, are time symmetric. They work just as well running backward as they do forward. Yet our everyday experience and the second law of thermodynamics, which states that entropy or disorder always increases, shows a clear arrow of time. Some string theory models offer a speculative but intriguing explanation for this. The explanation is tied to the expansion of the universe in the brain world scenario. Our three-brain universe is expanding. The idea is that this expansion itself is what defines the direction of time's arrow. It's the master clock against which all other processes, including the increase of entropy, are set. The universe is expanding because it was set in motion by an event like the collision of two brains in the ekpyrotic model. This initial event created a universe with low entropy, and the subsequent expansion is the process of that entropy increasing. Furthermore, string theory provides a microscopic reason for why information seems to be preserved as time moves forward. The holographic principle states that all the information in our universe can be stored on a boundary surface. This suggests that the universe is, at its core, a quantum system, and in quantum systems, information is conserved. The evolution of the universe is a unitary process, meaning it's reversible in principle. The apparent arrow of time and the increase of entropy are just statistical effects related to us starting in a very special low entropy state and expanding into a much larger, more disordered state. The fundamental process is time symmetric, but the specific state of our expanding brain universe gives time its apparent direction. It's a bold idea that links the largest cosmological scales with the deepest quantum principles to explain something we experience every second of our lives. Number 7, the unification of forces is an illusion of low energy. For decades, one of the biggest goals of physics has been to find a unified theory that describes all four fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces as different aspects of a single underlying force. String theory achieves this in a remarkably elegant way. It suggests that the reason these forces appear so different to us is because we are observing them at very low energies. In string theory, each force is carried by a particle that corresponds to a specific vibration of a string. At the incredibly high energies that existed just after the Big Bang, what physicists call the Planck energy, all these different vibrations would have been part of a single unified superforce. The strings were vibrating with so much energy that the distinctions between the different modes were blurred. As the universe expanded and cooled, the energy levels dropped. This cooling caused a series of spontaneous symmetry breakings. At certain energy thresholds, the unified force split. First, gravity separated from the other three. Then, the strong force broke away. Finally, the weak force and electromagnetism went their separate ways. It's like looking at a single unified object, a pencil. At a distance, it's just a pencil. But as you get closer equivalent to probing at higher energies in physics, you see it's made of distinct parts: wood, graphite, metal, and rubber. In string theory, the different forces we see are just the low energy remnants of this primordial unified state. The theory provides a framework where this unification happens naturally. All forces, including gravity, are treated on the same footing as different notes played by the strings. This is a significant advantage over the standard model, which successfully unifies three of the forces, but leaves gravity out entirely. String theory's ability to incorporate gravity and unify it with the other forces is one of its greatest strengths, and a primary reason why so many physicists have dedicated their lives to studying it. Number 6, some theories are in a swampland and can't be real. Not every theory that looks like string theory is actually a valid one. In recent years, a major research program within the string theory community has been to figure out which theories are mathematically consistent and which are not. The collection of inconsistent theories is called the swampland. The small set of consistent theories that can be derived from string theory live on a small island in this vast swamp called the landscape. This effort is crucial for making string theory more predictive. The idea is to find general principles that any viable theory of quantum gravity must obey. These principles act as rules that separate the landscape from the swampland. One of the most important proposed rules is the weak gravity conjecture. It states that in any consistent theory of quantum gravity, gravity must be the weakest force. This might sound obvious, as it's true in our universe, but it's a powerful constraint. It's related to the idea that black holes must be able to decay. If gravity were stronger than, say, electromagnetism, you could have small, stable black holes that would violate fundamental principles. Another swampland conjecture states that any space-time we live in must be temporary. It cannot be perfectly stable forever. This has dramatic implications for dark energy. Some of the simplest models of dark energy involve a perfectly stable de Sitter space, a universe that expands exponentially forever. The swampland conjectures suggest that these simple, eternal universes are not possible in a consistent theory of quantum gravity. Instead, dark energy must be driven by a field called quintessence that is slowly changing over time. This means the accelerated expansion of our universe will not last forever. It will eventually end, though perhaps not for billions or trillions of years. These conjectures are exciting because they are testable. If future astronomical observations show that dark energy is a truly constant cosmological constant, it would mean the swampland conjectures are wrong. But if they show that dark energy is changing, even slightly, it would be powerful evidence that the ideas coming from string theory are on the right track. Number 5, the constants of nature might not be constant. One of the most radical ideas that can be accommodated by string theory is that the fundamental constants of nature, like the speed of light, the charge of an electron, or the strength of gravity might not be constant at all. They might have changed over the history of the universe, and they might even vary from place to place. In string theory, the values of these constants are not arbitrary numbers. They are determined by the properties of the curled up extra dimensions. Specifically, the values are related to fields called moduli fields that describe the size and shape of the Calabi-Yau manifolds. If the shape of the extra dimensions changes, the values of the constants we measure in our 4D universe will also change. In the very early universe, these moduli fields were likely fluctuating wildly. As the universe cooled and settled down, these fields froze into place, giving us the constants we see today. This freezing process is what determined the specific vacuum state our universe occupies in the vast string theory landscape. But is it possible that these fields are not perfectly frozen? Could they be changing very slowly over cosmic time? Some theories suggest this is possible. If, for example, the fine structure constant, which governs the strength of electromagnetism, were changing, we could detect it by looking at the light from distant quasars. This light has been traveling for billions of years, and it passed through gas clouds at various points in cosmic history. By analyzing the absorption lines in the quasar spectrum, astronomers can measure the value of the fine structure constant at different times in the universe's past. Some controversial observations in the early 2000s suggested there might be a tiny variation, but more recent and precise measurements have found no change. However, the possibility remains open. If any of the fundamental constants were ever proven to be not so constant, it would be a revolutionary discovery and would fit naturally within the framework of string theory, where the constants of nature are dynamic fields, not fixed numbers. Number 4, our universe could have been born from nothing. The quantum mechanics allows for something called a quantum fluctuation. The uncertainty principle means that for very brief moments, energy can be borrowed from the vacuum to create pairs of particles and antiparticles, which then annihilate each other and disappear. Some physicists have applied this idea to the entire universe. In a quantum cosmology framework, which often uses tools from string theory, the entire universe could have begun as a quantum fluctuation in a pre-existing state of nothingness. This nothingness is not the empty void we might think of. It's the quantum vacuum, a sea of potential and fluctuating fields. The idea, first explored by physicists like Alexander Vilenkin, is that a tiny bubble of space-time could spontaneously fluctuate into existence. Under most circumstances, this bubble would be unstable and immediately vanish. But if the conditions were right, a process like cosmic inflation could take hold, causing the tiny bubble to expand at an exponential rate, growing from a subatomic size to a macroscopic universe in a fraction of a second. String theory adds a layer to this by describing the landscape of possible universes. The quantum fluctuation wouldn't just create any universe, it would create a universe in one of the 10 raised to the power of 500 possible vacuum states of the landscape. This process could happen all the time, with new universes constantly popping into existence, a process called eternal inflation. Our Big Bang was not a unique event, but just the moment our particular bubble universe started inflating. This creates a picture of a multiverse that is a vast, eternally inflating sea of space-time in which bubble universes with different physical laws are constantly forming. String theory provides the underlying physics for the different types of bubbles that can form, and quantum mechanics provides the mechanism for them to pop into existence from a state of pre-cosmic nothingness. Number 3, there might be only one fundamental force. While string theory unifies the four known forces, some interpretations go even further, suggesting that at the most fundamental level, there is only one force, or perhaps even no force at all. The concept of force might be an emergent property of the geometry of space-time and the behavior of strings. In Einstein's general relativity, gravity is not a force in the traditional sense. It is the curvature of space-time. A planet orbits the sun not because it is being pulled by a force, but because it is following a straight line, a geodesic, through space-time that has been warped by the sun's mass. String theory extends this geometric idea to the other forces. The extra dimensions in string theory are not just empty space, they have a complex geometry described by a Calabi-Yau manifold. The other forces, like electromagnetism, can be seen as manifestations of the geometry of these extra dimensions. An early attempt at this was Kaluza-Klein theory in the 1920s. It showed that if you add a fifth dimension to general relativity, the equations naturally split into Einstein's theory of gravity in 4 dimensions plus Maxwell's theory of electromagnetism. The electromagnetic force becomes a consequence of the geometry of the tiny, curled up fifth dimension. String theory is the modern, superpowered version of this idea. All the forces, not just gravity and electromagnetism, are ultimately described by the geometry of the full 10 or 11-dimensional spacetime. The different ways strings can vibrate are dictated by this geometry, and these different vibrations appear to us as different particles and forces. In this view, the universe is a symphony of geometry. Everything matter, and the forces that govern it is a consequence of the shape of all the dimensions, both large and small. Number 2, the universe may be a causal set of discrete points. A very deep and speculative idea related to quantum gravity research, including some approaches within string theory, is that space-time is not a smooth, continuous fabric. Instead, it might be discrete, made of fundamental, indivisible atoms of spacetime. This approach is called causal set theory, and it attempts to address some of the foundational problems of physics by replacing the continuum of spacetime with a vast but finite set of points. The key idea is not just the points themselves, but the relationship between them. The only fundamental structure is a causal order, For any 2 points, one might be in the past of the other, or they might be unrelated space-like separated. This network of causal relationships is what builds up the structure of space-time. The number of points in a region of space-time corresponds to its volume. The geometry and curvature we are familiar with are large-scale, emergent properties of this underlying discrete structure, just as the smoothness of water is an emergent property of a huge number of discrete H2O molecules. How does this connect to string theory? String theory traditionally works with a smooth space-time background. However, at the Planck scale, the very idea of a smooth manifold is expected to break down. Physicists believe that a more fundamental background-independent formulation of string theory is needed, one where space-time itself is not an input but an output of the theory. Causal sets provide one possible mathematical framework for what this underlying structure might look like. The holographic principle, which suggests that a volume of spacetime is encoded on a lower dimensional boundary, also hints at a discrete, pixelated nature of reality. The information is measured in bits, suggesting a fundamental discreteness. The ultimate theory of quantum gravity may involve a synthesis of these ideas, where the fundamental entities, perhaps strings or branes, live on an underlying causal set, and the smooth spacetime we know is a large-scale holographic illusion. Number 1. The theory has no adjustable numbers. The ultimate goal of a theory of everything is to explain the universe from first principles without any adjustable parameters. The standard model of particle physics is incredibly successful, but it has about 20 numbers, like the mass of the electron or the strength of the weak force that have to be measured by experiment and plugged into the equations by hand. The theory doesn't explain why these numbers have the values they do. In its purest form, string theory has no adjustable parameters. There is no dial to turn. The theory is just the theory. All the numbers we see in our universe should, in principle, be calculable from the theory itself. The value for the mass of the electron, for example, would be determined by the way a string vibrates, which in turn is determined by the geometry of the compactified extra dimensions. This geometry physicists hoped would be uniquely determined by the consistency conditions of the theory itself. The dream was that there would be only one way to build a mathematically consistent universe based on strings, and it would inevitably be our universe. This dream has been complicated by the discovery of the string theory landscape, with its 10 raised to the power of 500 possible solutions. This seems to reintroduce a massive amount of arbitrariness. However, many theorists have not given up hope. They believe that we are still missing a crucial dynamical principle that selects one specific vacuum state from the landscape. Or perhaps the vast majority of the landscape solutions are actually inconsistent part of the swampland for subtle reasons we don't yet understand. The pursuit of string theory is the pursuit of this ultimate explanation. It's a bet that the universe is not a random collection of arbitrary constants, but a unique and elegant mathematical structure. The hope remains that the wild and wonderful ideas of string theory, from vibrating strings and extra dimensions to branes and holograms, will one day coalesce into a final theory that explains not just how the universe works, but why it must be the way it is.